Water. All living things need it. Here is water in its natural habitat. But what makes up water? Everything in the entire universe is made up of elements. Elements are pure substances that can't be broken down further. They can be put together to make compounds. All elements have their own specific atom that gives them different characteristics. Atoms are very tiny things that are made up of electrons, protons, and neutrons. The protons and neutrons join together to form a nucleus, while electrons fly around the outside. The electrons move so fast at the speed of light that scientists decide to show them as a cloud around the atom. All atoms have electric charges. The protons give an atom a positive charge, and electrons give the atom a negative charge, while the neutrons are electrically neutral, so they don't have a charge. Atoms that have a neutral charge have the same number of protons, electrons, and neutrons. Some types of atoms have more neutrons than protons or electrons. These are called isotopes. Isotopes are used mainly because they give off radioactive energy, which happens when the nucleus of a radioactive isotope breaks down over time. Every nuclear power plant uses radioactive isotopes to produce electricity. Atoms have energy levels that hold electrons. The closer those energy levels are to full, the less an atom wants to interact with other atoms. For example, an oxygen molecule is walking along. It has 8 electrons flying around it. Its first energy level, which can hold 2 electrons, is filled and happy. The second energy level, however, can hold up to 8 electrons. For oxygen to be a happy atom and not want to interact with any other atoms, it needs 10 electrons. Because it only has 8, oxygen wants to meet other atoms and share electrons with them. Along walks a hydrogen atom. Hydrogen has 1 electron, which is half of what its first energy layer can hold. Hydrogen also wants to meet someone, so it can share electrons and fill up its energy level. When oxygen and hydrogen meet, they share all 9 electrons, and are happier, but still want at least 1 more electron so they can fill up their second energy level. A third atom, another hydrogen atom, sees oxygen and hydrogen together sharing electrons. He is a generous atom, so he shares his electron with them to fill up the second energy level. Because their energy levels are full, the new molecule, which is a group of 2 or more atoms, is happy. There are 2 hydrogen atoms and 1 oxygen atom, which go together to make a water molecule. But how are the atoms staying together to make the molecule? Why don't they just float away? Atoms are held together using ionic and covalent bonds. Ionic bonds are when an atom gives an electron to another atom. For example, there is a sodium atom and a chlorine atom hanging out. Sodium has 11 electrons and chlorine has 17 electrons. Sodium has 1 extra electron in its third energy level, and chlorine has 2 full energy levels, but a third level that is missing 1 electron. When the 2 atoms smash together, sodium gives its extra electron to chlorine, making them both happy. But remember how I said atoms have electric charges? Because the atoms now don't have the same number of protons and neutrons as electrons, they are called ions. When the sodium atom lost its extra electron, there were more protons, which have positive charges, than electrons, which have negative charges, so this ion has a positive charge. For the chlorine, it gained an electron, which gave it more parts with a negative charge, meaning the entire ion has a negative charge. Even though the 2 ions have full energy levels and the subatomic particles, which are all the things that make up an atom, are happy, they now have different electric charges. For electricity, things with negative charges and positive charges want to be closer to one another. Now that the sodium is positively charged and the chlorine is negatively charged, they are attracted to one another. They are now tied together by an ionic bond because of the opposite electric charges. There are also covalent bonds. Unlike ionic bonds, when an atom gives or takes an electron from another, covalent bonds are created when atoms share electrons with one another. Take our friends oxygen, hydrogen, and hydrogen's identical twin. They share atoms so they can all fill their energy levels, and then they're happy. Molecules use covalent bonds to hold atoms together. When 2 or more atoms come together, it can also be called a reaction. In a reaction, the starting materials are called reactants, and the ending materials are called products. There are billions of ways that atoms can go together to form molecules, but how are you supposed to remember what types of atoms and therefore elements there are, especially when there are 120 different elements and counting? The periodic table is here to help. The periodic table was invented to organize elements and give information about them. In every little box, there is an abbreviation or a short group of letters that stand for an element. In the upper left, there is an atomic number, or the number of protons, electrons, and neutrons that an atom of that element has. On the bottom, there is the atomic weight of an atom. On some periodic tables, the state of matter that an element is at room temperature is put on the table by changing the color of the abbreviation. For example, oxygen is a gas at room temperature, so it is red on the table, but gold is black, and it is a solid at room temperature. Horizontally, the atoms are put in order of the number of protons and electrons and neutrons that they have, except for the actinides and lanthanides, groups of elements that are placed below the table. The rows are organized by how many electrons the atoms need in total, and also tells you how many energy levels there are for those elements, and how many electrons can fit inside of each of those. The columns of the element show the period of the element, which tells you how many electrons that the element has in its highest energy level. The columns are named by what types of elements are arranged there. For example, the last column of the periodic table has elements called the noble gases because none of them want to share or give electrons to other elements. Those elements can go together to form other substances. For example, oxygen and hydrogen go together to make water. But it's not always that simple. The way the molecules are arranged plays a large part in the way that those molecules interact with others. In a water molecule, there are covalent bonds. The oxygen and hydrogen are pulled together by shared electrons, but the oxygen is pulling the hydrogen more strongly than the hydrogen pulls the oxygen. This is because the oxygen has more protons and electrons, therefore a stronger electric charge. This makes the shared electrons spend more time around the oxygen molecule than around the hydrogen molecule. Water molecules are shaped like V's. They have a large oxygen atom at the bottom and two smaller hydrogen atoms at the top. The oxygen atom, because of the shared electrons, has a slight negative charge, while the hydrogen atoms have a slight positive charge. This makes the water molecules into polar molecules, which are molecules that have opposite charges at opposite ends of the atom. Because they are polar molecules, water molecules all want to be next to each other. The hydrogen atoms each form bonds with other oxygen atoms and create hydrogen bonds. Without water, there would be no life on Earth. Water makes up more than 90% of your body. It gives living things energy and food and also makes sure that the Earth is still okay to live in. Two of the ways that water gives life are cohesion and adhesion. These are the main ways that water gives life to plants and trees. Cohesion is when molecules of the same type stick to one another, and adhesion is when molecules that are not the same type are attracted to each other. Here is an example of cohesion and adhesion working together to feed a tree. After it rains, there is a lot of water collected into the tree's roots. Evaporation pulls the water up the roots into some narrow tubes inside the tree. Cohesion makes all the water molecules stick together throughout the entire tree so they don't mix with anything else, while adhesion makes the water molecules stick to other molecules inside the tubes and not fall back down to the roots. Using cohesion and adhesion and also evaporation, the water moves through the tree up into the leaves, giving the tree food. Water can also moderate temperature. That means that the water can alter its own temperature to make sure that nearby things are okay and not too hot or too cold. For example, in some cities that are close to an ocean, the water cools down the warmer areas of the city and heats up some of the cooler areas. This is why some places near large bodies of water don't have snow or heat waves that often. Water does this by releasing energy. The energy that is released is called thermal energy. Water releases thermal energy in the form of heat. When you heat up water, the molecules inside move faster, and some hydrogen bonds between water molecules start breaking. The breaking of the bonds releases heat and makes the water absorb thermal energy. But when you cool water, it starts to make new hydrogen bonds and slows the molecules down. When all the molecules stop moving or begin to move in patterns, the water releases thermal energy as heat and eventually becomes cold enough to become ice. Water can also dissolve other substances. If you put water in a mix with other substances, you form a solution. For example, sugar water is a solution of water and sugar. If there is more of one substance in a solution, that substance is called the solvent. For example, if there is more water than sugar in sugar water, then water is the solvent and the sugar is called a solute, which is the substance that is dissolved by the solvent. When water is the solvent in a solution, it is called an aqueous solution. Water is the main solvent in a lot of solutions, especially in blood, sap, and almost every other drink you can think of. In blood, water dissolves the other substances and gives their nutrients to the rest of the body. When you drink or eat food, the other water in your body dissolves the food and drinks and sends those nutrients into your bloodstream. In an aqueous solution, a few water molecules break themselves apart and form ions. The ions that form are hydrogen atoms with a slight positive charge and negative hydroxide ions. Hydroxide ions are a mix of an oxygen atom and a hydrogen atom that has a negative charge. Some chemicals that can be added to a solution can add or remove hydrogen ions to an aqueous solution. One that adds hydrogen ions is called an acid, while a chemical that takes away hydrogen ions is called a base. Some bases also work by adding hydroxide ions, which join with the hydrogen ions to form water molecules. The more hydrogen ions in a solution, the more acidic it is considered. The less hydrogen ions or the more hydroxide ions in a solution, the more basic it is considered. Scientists measure how acidic or basic something is on a scale called the pH scale. The scale starts at 0 with the most acidic solutions and goes to 14 with the most basic solutions. The closer something is to 14, the less acidic it is. For example, grapefruit juice is pretty acidic. It has a pH value of 3. Aqueous solutions with equal amounts of hydrogen and hydroxide ions are called neutral solutions and have a 7 on the pH scale, right in the middle. In most living cells, like the ones in your body, there is a pH value close to 7. Molecules in cells are very sensitive to how acidic or basic they are. Even moving to a 6.5 or a 6 on the pH scale can be extremely bad for the cells of living things. That's why many biological fluids have these things called buffers. Buffers are there to help living cells regulate the changes in their pH. If a cell starts to become too basic, the buffers will get some additional hydrogen ions, which will add some acid and bring the pH down to a better level. If the cells have too much acidic chemicals, then the buffers will give some of the hydrogen ions away and bring the pH level back up to around 7. One very important example of buffers is in a person's blood, which has a pH value of 7.4. Some chemicals in your body make your blood become more acidic or basic than it is normally. Thankfully, buffers are there to make everything stay okay.